You!
Who, me?
Yeah, you! You should be adept in drawing 2D Lewis diagrams for molecules, but we have to understand that molecules in real life are actually 3-dimensional. In this episode of Tea Talks with Tianze, Eddie, and Andrew, we will be learning about the 3-dimensional models of molecules. And to do that, we need to understand electron domain geometry and how it correlates with VSEPR.
So the whole idea of drawing 3-dimensional compounds revolves around VSEPR, valence, shell, electron, pair, repulsion theory. It may look very intimidating, but it's actually quite simple. The theory outlines a position in which covalent molecules minimize repulsion between electrons.
Let us use an analogy. We have Andrew and Eddie, who are negative electron regions, and they don't like each other. Hence, they will want to be as far as possible from each other. However, I, as a nucleus, am friends with both of them, so I keep them from running too far away.
The structure of most molecules can be represented using electron domain geometry in the form of AXE. In this representation, A is a central atom, X is a number of covalent bonds, and E is a number of electron pairs. The first step in determining AXE is to determine the central atom. Usually, the central atom is the one with the lowest electronegativity. Recall your periodic trends. Electronegativity decreases down a family and increases across a row. Next, we will determine the number of bonds and lone pairs. To do this, we draw a Lewis diagram. If you forgot how to do this, refresh yourself with the last video. Afterwards, we simply add a subscript under X and E to represent their respective counts. Now to the main part of the theory, finding a molecule's 3-dimensional structure. In the following diagrams, the blue atom will represent the central atom, the red atom will be attached atoms, parallel lines will represent covalent bonds, and the green dumbbells will be unbonded electron pairs. Remember that all molecules want to be in equilibrium, and thus want the lowest repulsive forces between their atoms. Two unbonded electron pairs have the highest repulsive forces between them. The second highest repulsive force is between an unbonded electron pair and a covalent bond. Finally, the weakest repulsive force is in between two covalent bonds. This is why unbonded electron pairs can literally deform the angles between covalent bonds. Let us first look at this list without electron pairs. These are the relatively easy ones to visualize. AX2 is a linear-shaped molecule. It's basically still in the realm of the 2-dimensional world. The two atoms bonded to the central atom each have their own respective electron clouds, which are negatively charged and repel each other evenly. AX3 is similar to AX2. They are both linear planar and in 2-dimensional. But AX3 is split evenly in 3 ways, with each bond angle at 120 degrees. Imagine a pie chart split in 3 equal parts. This is what AX3 looks like. AX4, also known as a tetrahedral, goes into the 3-dimensional realm. Think of it as combining 2 molecules with a bond angle of 109.5 each in a 3D shape so that the angles between every atom is now 109.5 too. Every atom is equally spaced apart. We can think of the molecule like a triangular pyramid. Each corner of the pyramid corresponds with an atom in AX4. AX5 is basically a combination of AX3 and AX2 in a 3D form. First, we take a molecular shape for AX2, then we place a shape of AX3 perpendicularly to AX2. Imagine a molecule as one having 2 atoms at its north and south poles, and then 3 atoms equally spaced around the equator. Now we get a sort of trigonal bipyramid shape. The 3 atoms around the equator can link up to the atoms at the poles to form 2 triangular pyramids. AX6 is similar to AX5. We start off with 2 atoms in AX2 configuration. Imagine them like before, as placed on the north and south poles of the atom. Now instead of 3 equally spaced atoms around the equator, we have 4 of them, like a square. AX6 is basically a octahedral, because when you link up the atoms, it forms 2 square-based pyramids opposite of each other.
This is a shape similar to AX3. However,
instead of having 3 covalent bonds, there are 2 covalent bonds, and 1 pair of lone electrons. As a result, its structure is bent with a bond angle of 114.5 degrees. You may wonder, why is the bond angle smaller than that of AX3? This is because lone pairs repel more than covalent bonds. Lone electron pairs repel electrons more strongly because they are closer to the nucleus than covalent bonds. AX2E2. This structure contains 2 covalent bonds and 2 lone pairs of electrons. You may think about this shape in terms of a tetrahedral without 2 of the vertices. The bond angle is 104.5 degrees, which is slightly less than that of AX4 because the lone pairs repel more. Finally, AX3E. This is a tetrahedral structure without 1 vertice or covalent bond, which is replaced by a lone electron pair. It forms a trigonal pyramidal shape. AX2E3. This variation of AX5 is a linear one. The 2 atoms are linearly spaced as the 3 electron pairs repel the 2 atoms equally and are arranged in an AX3 pattern perpendicular to the 2 atoms. X3E2. This variation is called the T-shape. Remember how AX5 is composed of AX3 and AX2? Well, the electron pairs occupy 2 of the AX3 atoms, but the repulsive forces are stronger than normal, so the 2 AX2 atoms are now no longer linear. In fact, the angle between the pole atoms are pushed from being perpendicular at 90 degrees to the AX3 atoms to being only 87 degrees relative to each other. AX4E, this variation is called the seesaw shape. In this case, the electron pair replaces 1 atom of the AX3 atom. The angle between the 2 remaining AX3 shaped atoms is 101.6 degrees. AX4E2. AX4E2 is similar to AX6 since it has 6 components, but 2 electron pairs on the north and south poles balance out their charges. The rest form a 90-degree angle with each other on the x-axis, resulting in a tetrahedral planar shape. AX5E has a similar shape to AX6, except that there is an electron pair instead of a covalent bond in the molecule. This electron pair repulses the electron in the covalent bonds away, so the bond angle that was originally 90 degrees is now slightly less than 90 degrees. But since it's only 1 electron pair against 5 covalent bonds, the bond angles will only be slightly less.
Okay, you ask, why does this matter? Well, once you know the 3D structure of a molecule, you will be able to roughly predict certain properties such as polarity, dissolvability, attraction, freezing point, melting point, boiling point, and on and on and on. That is, you will be able to compare molecules with different structures.
Given the electron domain geometry and the shape of the molecule, we can figure out if a molecule is polar or non-polar. Molecular polarity primarily depends on 2 things: bond polarity and the shape of the molecule.
A molecule is polar when there is uneven distribution of charge within the molecule. So one end of the molecule may have a dipole moment and be slightly more positive, and the other end more negative. We can determine the distribution of charge by looking at an atom's electronegativity. For example, in the molecule cyanate, oxygen has a higher electronegativity than nitrogen. Therefore, it will have a larger pull on the shared electrons. Thus, the oxygen side of the atom has an induced negative charge, and the nitrogen side of the atom has an induced positive charge.
For the molecules AX2, AX3, and AX4, because of the way the molecules are shaped, check if all the non-central atoms are the same. If they are, then the molecule is non-polar. If they aren't, then the molecule is polar. Here's a list of different types of planar AX2 and AX3 molecules that will be useful later on in determining the polarity of AX5 and AX6. For AX5 and AX6, the atom is split into 2 distinct sections. We'll split these and call them the vertical and horizontal components. Now we simply apply the rule for determining polarity from planar molecules like AX2 and AX3 to each component separately. If both the polar and horizontal components are nonpolar, then the molecule is nonpolar, because the charge in each component cancels out to 0. Otherwise, it will be polar. For the molecules that have extra electron pairs, let's invent a term right now and call it parts. Parts can either be non-central atoms or unbonded electron pairs, so something like AX3E2 would have 5 parts. Anything with 4 or less parts to the molecule cannot be split into 2 components, horizontal and vertical, and if one or more of these parts includes an unbounded electron pair, then it's polar.
Now, this idea of parts gets us back towards the realm of EDG. In chemistry, a part is actually known as an electron domain, which is basically just an electron pair, but does not matter if the pair is bonded or not. When finding the electron domain geometry of a molecule, we simply treat the lone electron pairs as bonded pairs. Then we simply name the molecule as we would if its lone electron pairs became bonded pairs. For example, AX3E2 has 2 unbonded electron pairs and 3 bonded electron pairs, so its electron geometry would be 5 bonded electron pairs, or AX5, and would thus be called trigonal bipyramid. However, its molecular geometry is still T-shaped, and we mostly still refer to AX3E2 by its molecular geometry instead of its electron domain geometry.
Anything with 5 or 6 parts can be split into 2 components and resembles AX5 or AX6. For molecules with unbonded electron pairs, which hold a very strong negative charge, to be nonpolar, we need the electron pairs to cancel each other out. In AX2E3, if the horizontal component is completely filled with electron pairs and a vertical component charges cancels out to 0, then the molecule is nonpolar. In AX4E2, it works out in a very similar fashion. If the vertical component is completely filled with lone electron pairs, and the horizontal component's charges cancels out to be 0, then the molecule is too nonpolar. Due to the nature of their molecular shapes, AX2E3 and AX4E2 are the only VSEPR shapes with 5 or 6 parts that can ever be polar. If either a vertical or horizontal component has unbonded electron pairs, but is not completely filled with more unbonded electron pairs, then the molecule is considered polar. Okay, so now that we've finished learning about VSEPR and polarity, what does this lead us to?
Formal charge is a procedure by which chemists can find the charge at a particular point of a molecule. If all atoms have equal electronegativity, then the formal charge will be 0. Otherwise, the formal charge can be calculated with the following formula. Formal charge equals number of valence electrons in a neutral atom minus number of non-bonding electrons plus half of the bonding electrons. When there is a separation in the molecule, it takes energy. Thus, we want the lowest separation of charges, and hence, the lowest formal charge will create the most stable Lewis structure.
But what does each element within our formal charge formula mean? Take, for example, this bonded oxygen atom in H2O. To find the number of valence electrons in oxygen, we simply consult the periodic table to find the number of electrons in the valence shell. To find the number of non-bonding electrons, we simply count the number of lone electrons represented by dots on the diagram. To obtain the number of bonding electrons, we simply count the number of bonds formed by oxygen multiplied by 2, but we also have to divide it by 2 again according to the formula.
You may have noticed that sometimes we can have Lewis diagrams with multiple possible structures. Consider the molecule H2CO2. There are 2 possible Lewis structures for this molecule. Each Lewis structure has the same amount of bonds. We can determine which is better by finding out which has the least formal charge. Using the formula above for the Lewis structure 1, the formal charge is the following. Using the formula above for this Lewis structure 2, the formal charge is the following. So in this case, the following Lewis structure is more stable and is hence the chosen one.
This leads us to our next video on intermolecular forces, dipole-dipole, hydrogen bonding, and London dispersion force.
Paul's Chem videos are filmed here in Ottawa, and it's made possible by the support of our sponsor, Miss Paul, a long-standing chemistry teacher at Crombie Secondary School adored by her students. We hope you enjoyed our video. Remember to leave a like, and if you can't, thank you for watching anyways.